2. This is another circle problem. So we're going to have a circle. And the area, here's what you need to do when you're dealing with these. Look for what they're talking about. The area increases at a rate of 9 pi meters squared per minute. So dA dt is going to be 9 pi meters squared per minute. How fast is the radius of the spill increasing? So whenever it says like how fast, and it says how fast is the radius, so that's going to be a dr dt. So when you're looking at these problems, they're talking about whether or not area is increasing, or what's the rate at which something is increasing or decreasing, or how fast. All of those are indications that you're talking about some type of rate of change, which means you're talking about a derivative of some kind. And since we're talking about a circle, and we know at r equals 10 meters, we need the area of the circle. So what's the area of a circle equation? Pi r squared. Now, take the derivative of this equation with respect to time. So it's just a bunch of chain rules. We take the derivative of every variable, and then we use the chain rule, which would just be d whatever the variable is dt with respect to time. So what's the derivative of just a? It'd be 1, so it'd be dA dt, which is like your rate of change, which is like delta A over delta t, which is like your slope, rate of change, that type of thing. Now, pi is a constant, so I just really care about the derivative of 2r, or r squared, which is 2r. So I'll get 2 pi r, because I put the 2 in front of the pi. Now, chain rule. dr dt. So every single time, you're going to end up using a chain rule. Now, what's the derivative of the area? Well, no. Just the derivative of the area. If you looked at it and see 2 pi r, that's the circumference of the circle. So the derivative of the area is their circumference. So there's this weird relationship between, not weird, but a relationship between area and circumference. And believe it or not, you would find out that there's, if you find like the area of a rectangle, take its derivative, it ends up being the perimeter. It's kind of cool. All right, but now, dA dt is 9 pi. That's equal to 2 pi. Now, the radius was what, 10? Times dr dt. So this is 9 pi is equal to 20 pi times dr dt. Divide both sides by 20 pi. So I'll put the answer over here. Dr dt is equal to, pi's cancel out, you get 9 over 20. Now, what's the rate going to be for the change in radius? The change in area was meters squared over minutes, so meters per minute. Yes, sir. 10 was given to us in the problem. Questions on that? Alright, next one. A conical paper cup, a cone, like one of those cones that you get. Like a snow cone. That's what conical means. Now, the height and the radius are both 10. But water is flowing in. I get to draw pictures. Woo. There's your radius, and there's the height at that point. Now, when you're using a cone, what's the equation for the volume of the cone? 1/3 pi r squared h. And the problem with this is, a lot of times, whenever you have a conical problem or a cone problem, you either want to get r in terms of h, and you want to change it all into h's, or you want to change the r or the h into an r and have all r's. So you only have one variable as opposed to multiple variables. So in order to do that, what you need to do is you need to use similar triangles. And that's your R, that's your H. This whole thing is 10, and that's 10. And it says, it doesn't say assume it's a right triangle, but we're going to assume it's a right triangle. What? Yeah, this is H. So this is basically taking a cross-section of the cone at that point. Now, in order to do this, since you have similar triangles, sides are proportional. And a lot of problems, especially when you get on the back page and you're looking at that guy walking away from the street light, it's a problem that's very similar to this because it's going to use similar triangles. You're going to use similar triangles a lot in these types of problems. Now, we're going to set it up. And I take the radius. I like to go small to big. Like R over 10. Because if you take the ratio of corresponding sides. Now, what would be the corresponding sides? H and what? H and 10. You do a cross product, you get 10R is equal to 10H. Divide by 10, R is equal to H. So you're going to want to do something like this every single time. You want to set this up, and it just so happens that the height and the radius are the same. So the height was 10, the radius was 10, but now the radius and the height, as the water level increases, is going to be the same as well. So I can go back to this equation, and since I know the water level rises at a rate of 2 centimeters per second, and what's the rate of the water being poured into the cup when the water level is at 8 centimeters? So we're talking about H's in this case. So it's saying dH dt is equal to 2 centimeters per second, and H is equal to 8 centimeters. So that's why I want to do this. Pi, and then I'm going to change the R to H squared times H. Yeah, that's what I'm going to do. So we get 1/3 pi times H cubed. Yes. We will. Absolutely. But first you got to build that equation, and now we've got it all in terms of H's. We got rid of our radiuses, and we have everything in terms of H's. And we did that by finding the relationship between the radius and the height using similar triangles. And this is something you'll have to do over and over and over again. So now, take the derivative of this. Derivative, we want dv dt is equal to 1/3 pi times 3h squared times dh dt. And remember, since none of these variables are time, we always have to do a chain rule, dh dt in that case. Yes? These are coefficients. So if it was 1/3 plus h cubed, then it would be 0. But since it's multiplying by it, we multiply it by it still. So the 3's multiply out, and we want what rate is the water being poured in. So this is actually what we want. We want dv dt. So the 3's divide out. I'm left with pi times, what's my h squared? What's h? H is 8. So I want 8 squared times 2, and that'll be centimeters per second. And this is 8 centimeters squared. So what's 8 squared? 64 times 2? 128 pi centimeters cubed per second. And that's my dv dt. Now, when you have a problem with a cone, they're either going to ask you about the rate of change of the volume, the rate of change of the radius, or the rate of change of the height. And every problem is going to be a variation of this, where you have to set up the similar right triangles, and then you have to figure out and basically replace h with r, or r with h, and get an equation in one variable over here on the right-hand side. Yeah?
Alright, so if we got like 2r equals h, we put like 1/2 h in the...
Yeah, because r would be equal to h over 2. And so we change that, but that would be squared, so it would be r squared over 4. Because since it's r squared, it has to be h over 2 squared. That quantity squared.
Where did you get 8 centimeters
8 centimeters squared. The water level, it said here the water level was 8 centimeters. So that was my h value, so I put that in there. And then I squared it.
What about the 2?
The 2 was given over here, and it says the water rises at a rate. So the variable that talks about the rising is the height. And you just plug that in. Because 8, that would be my dh dt. That's the rate that the height is changing. So the biggest thing is deciphering what rates mean what. All right. What? A spherical balloon, that's a 7-foot tall person, is inflated so that the radius increases at a rate of 2 over r centimeters per second squared. So this is telling me that the radius is changing at this. So what do you think this is going to be? dr dt. That's equal to 2 over r centimeters per second. And it tells me that r is going to be equal to 4 in the equation. So now I need to know what the volume of a sphere is. So, anybody remember what this is? Four-thirds pi r cubed. And now, all I have to do is, it says, how fast is the volume changing? So, how fast is the volume changing is going to be dv dt. So, what's the derivative of v? Well, hold on. Question. Yes. You should know the whole. You should know this. Oh yeah. You need to know them all. They're in your book. They're like on the back page of your book. Alright, so dV/dt is going to be equal to 4/3 times pi times 3r squared times dr/dt. So dV/dt is equal to 4. The 3's divide out, so 4 pi r squared times dr/dt. Now, if you take a look at this equation 4 pi r squared is the surface area of a sphere. So the derivative of the volume gives you surface area. So again, we have a connection between the two functions. Just like we had before when we were dealing with, I think even with a cone, if you take the derivative of it, that's the surface area of a cone. So volume, the derivative of the volume is equal to surface area. It's kind of like derivative position is equal to velocity. Derivative of velocity is equal to acceleration. Well, for shapes, you go with volume. Derivative of volume is surface area. So derivative of surface area is something totally different after that. I don't even know what that is. I don't think that's something we even measure. So now we plug in what we know. And I'm going to go over here and plug in what we know. I know nothing about dV/dt, so that stays. 4 times pi times r squared, so r's 6. No, it's 4. I was thinking 16 already. Sorry. I do that all the time. 16. And now I need dr/dt. It'd be 2 over 4, which is equal to 1/2. That's your dr/dt. So it'd be 1/2. 1/2 of 4 is 2. 2 times 16 is 32. So dV/dt is equal to 32 pi. Now, is it going to be centimeters squared or centimeters cubed? Cubed. Because remember, when you're talking about the change of volume, we're talking about a volume. So it'll be centimeters cubed per second. If we were talking about the change in radius, dr/dt, then it'd be centimeters per second. Or if we're talking about the change in area, it'd be centimeters squared per second, per time, whatever that is. So, that's the next one. Let me ask, so far, are these horrific? Hopefully the answer is no, because all you're doing is you're taking an equation and then you're taking respect with everything, or taking the derivative with respect to time for everything. Yes, ma'am. No. No and no. No and no. All right. Last one. I'll be honest, this one always shows up on one of my tests. A 7-foot tall person is walking away from a 20-foot tall lamppost at a rate of 5 feet per second. Assume this scenario can be modeled with right triangles. What's the rate of the length of the person's shadow? So if this is 20, here's what's going on. Because this would be the tip of the shadow. There's your 7-foot tall guy. So over here is your shadow. because the light is going this way. So he'd be blocking the light there. Now, here's what you do to set this up. And all of these problems are set up the same way. Let this part be x. The distance between the post and the person, let that be x. And let this distance here be y. And this guy here is going to be y minus x. Does that make sense?
Yes.
For now. Alright, so what I'm going to do is I'm going to, the only thing that we have, you can either use the Pythagorean theorem, which probably won't work because I guarantee you it won't work, but we have similar triangles. Yes? When, at the end. We want to model it generally at first. So what we want to end up, yes?
Isn't x 60 feet?
It is, but we don't want to put that in right away. You never want to put the values into the picture.
Yeah, but don't you need x to calculate y?
Eventually you will. But what we want to do first is we want to model it for any value of x and any value of y. And that's the biggest thing that you guys need to kind of let go of, is because we are so used to just taking numbers and plugging them in and going with it. If you were to plug in the 16 for x and we start taking derivatives, you start getting derivatives that are equal to 0, and then all of a sudden nothing's changing and the rates of change go away and we don't get the accurate picture. So we always plug in at the end of a problem. Yeah, at the end of the problem, we'll plug them in, but not at the beginning of the problem. Now, similar triangles. Anytime you're walking away from a flagpole like this or a light pole or anything like this, it's going to be similar triangles. So I'm going to get 7 over 20 because I took this part right here over this part. And now what I'm going to get is this part for the small triangle and that part for the big triangle. So this is going to be equal to y over x over y. So similar triangles give me this ratio. Everybody okay with that? Alright, now, next thing we do, solve for y. Do a cross product, 7y is equal to 20y minus 20x. Everybody okay with that? I'm going to subtract the 20y from both sides. Bless you. So I get negative 13y is equal to negative 20x. And then I divide that, negative 13y, negative 13, not by y, negative 13. So y is equal to, no, that was 20 over 13x.
Can we plug in x now?
Not yet. Not yet. Now take the derivative of this. Sorry. dy dt is equal to 20 over 13 dx dt. And now I can figure out what dy dt is because I know what dx dt is. Because it says we're walking away. This is your distance from the light pole. So dx dt. So dx dt is going to, it says person is walking away at a rate of 5 feet per second. So that's going to be here. So you get 5 feet per second. So that's your dx dt, because that's how that rate is changing. Yeah, there's your pole, there's your person. The distance is changing at 5 feet per second. So we go back over to here, we get dy dt is equal to, what's 20 times 5? 100 over 13. And now we're getting into weird fractions. 100 over 13, that would be feet per second. And I'm running out of actual space, so I need some more white paper. All right, question. Yeah. We didn't have to use. Actually, no. You never have to use that 16. But we're not done. Here's the thing: you're not done. What's the question asking? What? We want the rate of the shadow changing, don't we? So the shadow is equal to y minus x. So I want to do dy minus x dt. I want to take the derivative of the shadow to find the rate of the shadow, which will end up being dy dt minus dx dt. I see people shaking their head already. It's all right. Just kind of go with the problem. Then I'm gonna take it and I'm gonna go step by step for it and what we did. So hopefully it makes sense. Now, do we know dy dt? 100 over 13 minus, I know dx dt is 5. So if I want to make this into a fraction over 13, I got to multiply it by 13 over 13.
It's 65.
65 over 13, so I get 65 over 13, which is 35 over 13. Now, is x in feet or is x in something else? So it's feet per second.
Where did you get the 13 over 13?
I needed to make 5 into a fraction, so I could. This would have been 100 over 13 minus 5. Which, if we had a calculator, which would have been just fine. But if you don't have a calculator, then we have to make it into a fraction with like denominators. So that's what I did the 13 over 13 for. Now, if I zoom this out and I take a look at the whole thing, what I did is I drew a picture. Of similar right triangles. That was the first thing I did. 2. proportions to get an equation y equals something in terms of x. So I did x and y. Then took the derivative. To get dy dt and dx dt. And then 4 found the rate of change the problem wanted. Now, like I don't know if I've said this. This one, when I first started reteaching calculus, or teaching calculus for the first time, I'll be honest, this one took me a little bit of time to grasp and to get my head to wrap around. But once you embrace the idea of the similar triangles, and the similar triangles always end up being the same thing, the only not the only variation, but a variation you could use is this.